Myself, I'm Bhanu Prasad, working as assistant professor in Department of Mechanical Engineering in MBA College of Engineering and Technology. Today we will discuss about stability diagram. So in our previous lecture, we will discuss about introduction of the stability diagram one. So see here, stability means stability diagram stands for time temperature transformation diagram one. So it is also called as the isothermal transformation diagram one. So the stability diagram also we can call as the isothermal transformation diagrams. So another name one. So next, what is the definition of the stability diagram means? So stability diagram is gives the kinematics of isothermal transformation one. So it gives the kinematics of isothermal transformation it is given. So that's why we can call as it is one of the 3D diagram one. So see here, complete diagram of the 3D diagram one. So it is the 3D diagram, Amma. So in this 3D diagram, you can see single line definition one 3D diagram here. This diagram is nothing but austenite transformation, Amma. So we have the iron equilibrium diagram one. So iron equilibrium diagram one, the austenite phase is gamma one. So the gamma is transforming here. The gamma is nothing but here. So austenite one. The austenite is transforming like this one. So like this means the transformation, the austenite transformation is starting from here. The austenite transformation is ends from here. So it is the between starting is 0% onwards. So this line is 50% is one. This is a 100% transformation one. The austenite is completely transforming into different phases one. So we can see in this diagram one. So see here it is the time one. So it is the temperature. So it is see here 0 to 150 degrees onwards, we can call as this completely portion, we can call as gamma Martinez side one. So next one, so 150 onwards, we can see 150 degrees to, we can see here. So 500 degrees centigrade onwards, we can see gamma Banite one. So it is a gamma Banite one. So next one, 500 to 500 degrees to, we can see here. So up to 700 degrees onwards, we can see it is a gamma Parallite one. So it is a complete transformation one. The austenite is completely transformed into Parallite structure one. So that is a major structure. The final structure is Parallite one. So the austenite is totally changes to Parallite one. So here transformation begins one, it is the ending one. The final one is Parallite one. So before inwards, we can see austenite here. So see here, it is a Banite one. So the temperature lies between 250 to 500 degrees onwards. So it is the Banite one. So Banite structure we are getting here. So in Banite one, we can see upper Banite, it is a lower Banite one. So this temperature 400 degrees onwards, we are getting the Banite structure one. So the 400 degrees above one, we can call as upper Banite one. 400 degrees below one, we can call as lower Banite one. So see here, it is the one. So it is a gamma Martinezite one. So there, so it is see here, it is a Martinezite 50% one. So it is a Martinezite 90% one. So the transformation is changing here. So here onwards we can see. So Martinezite structure this one. So it is a 50% Martinezite we can observe here. So it is a completely 90% one we can observe. So it is a completely 100% Martinezite structure this one. So when we are cooling this one like this one. So when we are cooling this one, so automatically we are getting. So Martinez structure we are getting this line one. So this line onwards 50% Martinezite one. So it is 90% Martinezite one. So it is a MS 100% Martinezite this one. So it is a diagram. So it is the hardness we can see here in this one hardness one. So temperature we have we can using here 0 to 800 degrees centigrade we are using here. That time is nothing but 0 to 10,000 seconds we are using here. Comes to here detailed explanation of this diagram one. So see here it is a simple diagram. The austenite is changing to Parallite here. The austenite is transformed to Parallite. How the transformation is changing means here onwards the transformation will be begins here. So this line is 50% transformation. This one dotted lines. So comes to this line is 100% transformation will be here. So see here after then the austenite is changes to Parallite one. So see here detailed explanation of this diagram one. So time temperature transformation diagram is a plot of the float of temperature versus logarithmic of time for a several steel alloys of definite composition. So it is this diagram is a float of temperature versus logarithmic time of a steel one. So steel alloy one. of a definite composition, definite composition, when the temperature and time based on the composition will be changing here. Why? Because so first one is 0% one, next one is 50% one, next one is 100%. This transformation is going on. So 0, 50, 100% one. The composition also changing here. So simultaneously here we can observe here in this particular diagram one, the composition will be changing here, structure will be changing here, properties also changing here. So this diagram one, so three functions are changing this in between this transformation onwards. The three functions are changing here. So the structure will be changing here, the properties changing here, the structure, properties, and next one is composition one. These three are changes we can see, we can observe in this diagram one. So next one is, see here. So it is used to determine, it is used to determine when the transmission is begins and ends for a isothermal at constant temperature. So heat treatment of a previously arsonized Li1. So it is determined. How can we determine the tributary diagram means at constant temperature onwards, the transmission will be begins and ends. We can see on heat treatment of a previously arsonized Li1. So after then we can find out the tributary diagram. It is one of the experimental procedure here. So we can do the lot of experiments here. After then only we can get the perfectly, we can get the tributary diagram here. Time, temperature, transformation, we can see clearly on this graphical diagram one. So like this one. When the experiment is completed, so after then only when the transformation is begins and ends, so we can see after then only we can see this structure one. When the transformation is not begins, not ends, we cannot see this graphical representation one. The complete process is the process is completed one. After then we can visible on tributary diagram one. So see here, when the arsenide is cooled slowly to a temperature below lower critical temperature one, the structure is that is formed as perlite one. So when the arsenide is cooled slowly to the below the critical temperature one, the structure we are getting is perlite one. So it is the perlite structure. When we are cooling one, we can getting it is a transmission begins here. It is a 50% transmission, so 100% transmission. After final we are getting a perlite one. From transmission is begins here, ends here. The final we are getting perlite structure. So that is the definition, amma. So see here, as the cooling rate increases, the perlite is transformation temperature gets lower one. As the cooling rate increases, the transformation temperature gets lower one. So next one is so lower means the cooling rate is increasing on, temperature will be reducing here. So gets lower is nothing but, so when the cooling is, we can do for rapid cooling one, automatically what happen. So rapid cooling is nothing but we can go for water cooling one or liquid cooling, any liquid cooling, water cooling or lubricant oils cooling. So automatically what happen. So the cooling rate is increasing one, automatically the temperature is reduced very fastly also. So based on the cooling onwards, the temperature also getting very lower one. So that the microstructure of the material is significantly alternated as the cooling rate increases. So how we are getting the microstructure about this diagram means, see here, the microstructure of the material is significantly alternated as the cooling rate increases one. So when the cooling rate increases one, automatically we can get the one microstructure one. So when the cooling is not rapidly one, so not is alternative one, so we cannot get the one structure one. So by the heating and cooling a series of samples and the history of the arsenide transformation may be recorded one. So see here, the microstructure of the material is significantly alternated as the cooling rate increases. By the heating and cooling a series of a samples and the history of the arsenide transformation may be recorded one. So the arsenide transformation, it will be recorded when we are heating, when we are cooling. So when we are heating onwards, cooling onwards, the structure will be changing here. The transformation begins onwards, end onwards. The total structure we are recording here, tributary diagram onwards. So the tributary diagram indicates when a specific transformation starts and ends, and it is also shows the when the percentage of transformation of arsenide at a particular temperature is achieved one. So the tributary diagram indicates when the specific transformation starts and ends. So when a specific transformation is starting, it can shows, and it will be shows, and also shows when what the percentage of transformation of arsenide as a parallel temperature is HU1. So when the transformation is begins onwards, we can see the 0% is 1. So when the transformation is ending onwards, we can see 100% changes the microstructure. So that is nothing but totally parallel we can see here. So it is the one of the explanation. So see here, it is the arsenate structure. The arsenate structure is transformed to parallel. So it is a parallel structure. It is arsenate structure. It is a parallel structure. We can see here. So next one we can see arsenide is stable at temperature above the lower critical temperature, but unseen below lower critical temperature. The left curves indicates the starting of a transformation, and right curves represent the finishing of a transformation. So see here. So in this block diagram, left 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 diagram, right one, left curve, right curve. So this left curve indicates the transformation begins one. So these right curves indicates the transformation will be ends one. So that is the point here. So left curves indicates the starting of the transformation, and right curves represent the finishing of the transformation. The area between the two curves indicates the transformation of arsenate to different types of crystal structure. So in the area between these two curves, so the transformation begins and the transformation will be ends between these two curves. So it indicates the transformation of the arsenate to different types of crystal structure. So the transformation begins and onwards, we can see the different types of structure will be changing here. Different types of structures we can see on block diagram. So see here the structure, how the structure will be changing means arsenate to parallel one, arsenate to marsenite one, so arsenate to bainite one, bainite transformation. These three types of transformations we can see on between the transformation starting to ending onwards. So first one is arsenate to parallel is changing. So arsenate to martenite is changing. So arsenite to bainite also it is changing. So the isothermal transformation diagram shows the gamma to transformation. A is rapid one, the speed sound D1. The percentage of the transformation is depending on the temperature only. So the percentage of the transformation is depends on the temperature only. When the temperature will be reduced very fastly, so that the percentage also changing one. So the reduce when the cool fastly one, automatically the percentage also changing one. So slowly it cooling one, the percentage also it is changing slowly one. When the cooling very fastly one, the percentage is also changing very fastly. So that is the definition. So next one we can see here, upper half of triviality diagram, austenite to parallel transformation. So upper transformation is nothing but, so see here in this diagram, is upper line one. So this one, it is the lower one, it is upper one, it is the lower transformation, the upper transformation one, this line parallel. This red line onwards, it is upper transformation one. So this line onwards, lower transformation one. Upper transformation, the upper half of a trivial diagram, austenite to parallel degrees transformation. So see here, so it is the temperature, it is the time. So transformation begins 100% austenite here. So this line. So the first curve, left curve one. So this curve represents the 50% transformation, 50% austenite plus 50% parallel we can observe here. So it is the upper half of the triviality diagram one. So next one we can see parallel one, completely it is changing. Transformation ends here, 100% parallel one. So in this diagram, so see here in this diagram one, upper transformation onwards, it is the starting line. So it is the transformation begins here. Here onwards we can observe 100% austenite one. So in this line, 50% austenite, 50% parallel we can observe here. So in this last line we can observe here, so 100% parallel one. So it is the upper transformation one. So upper half of triviality diagram, austenite to parallel transformation one. So see here, as the indicates, when it is cooled to a temperature below the lower critical temperature, transform to other crystal structure due to its unstable nature one. So you can see here, at lower critical temperature onwards, we are cooling one, so we are getting this type of structure one. So that is nothing but, so parallel we are getting final structure. So that is the point here. So a specific cooling rate may be chosen so that the transformation of arsenate can be 50% and 100% extras one. So we can observe in this block diagram one. So 100% arsenate we can see, 50% arsenate also we can see. If the cooling rate is very slow one, such as annealing process one. So if the cooling rate is very slow about the triple diagram, so that is nothing but one of the annealing process one. So the cooling curve passes through the entire transformation area and the ends the product of this the cooling process become 100% parallel one. So the cooling curve passes through the entire transformation area and ends the product of the cooling process become 100% one. So that is nothing but parallel one. When the transformation will be ends 100% onwards, we can observe clearly. We can observe the structure is nothing but parallel one. So before onwards, we can observe that is a arsenate one. So 100% transformation is completed. So we can see here parallel one. So in the other words, when the slow cooling is applied, all the arsenate will transform to parallel one. So it is done on very slow cooling rate. When we are using the slow cooling rate, after then the arsenate is transformed to parallel one. If the cooling curve passes through the middle of the transformation area, the end product is 50% arsenate and 50% parallel one. So the medium one, the first curve is transformation begins. So that curve onwards we can observe 100% arsenate. Comes to the second curve. Second curve is nothing but dotted lines. The dotted line onwards we can observe 50% arsenate, 50% is parallel one. So the right curve we can observe 100% is 100% is parallel. We are getting that one. So that is the point definition, which means the at a certain cooling rates we can retain parts of the arsenate without transformation into a parallel one. So it is called, it is the upper critical transformation one. So next to see here, lower half of the triple diagram one, arsenate is changed to martensite and bayonet transformation one. So lower one. So it is the lower transformation amount. So see here, it is upper transformation. Arsenate is changes to parallel one. So it is lower transformation onwards. The arsenate is changes to bayonet and martensite one. So the lower one we will discuss about this diagram one. So it is lower half one. So see here, it is a lower one. So unstable arsenate we can observe here. So MS martensite starts from here onwards. So the martensite starts from here onwards. So here this one is 50% martensite transformation one. So see here, this line is nothing but martensite finishing one. So see here, first one is unstable arsenate we can observe. Unstable is nothing but that is not a stable one. Stable arsenate is we are not getting here. So here onwards the martensite starts from here. Transformation, the arsenate is transforming here onwards. So we are getting martensite starts. So here in this line one we are getting 50% martensite transformation. So comes to this line 100% martensite we are getting here. The martensite transformation is completed here. So finally we are getting martensite finishing one. So it is the time, it is the temperature. So it is the one of the transformation at the lower half of the 3D diagram. It is the lower half of one. So that one is it. This diagram is upper half. Upper half is nothing but we can observe arsenate is changes to parallel one. But lower half we can observe arsenate is changes to bayonet and martensite one. So it is the bayonet one. So bayonet onwards it is changes to complete martensite finishing one. So it is the diagram one. So next one we can see if a cooling rate is very high, the cooling curves will remains on the left hand side of the transformation starts curve. So if the cooling rate is very high, so very low high when we can observe means left side of the left side we have the left side and right side we have. So left side of the transformation starting curve one. So in this case all the arsenate will transform to martensite one. If there is no interaction in the cooling, the end product will be martensite one. So the left curve we can observe. So the left curve onwards we can observe. So very fast cooling one, high cooling we are getting one. So that's why in this case all the arsenate will transform to martensite one. So if there is no interaction in the cooling, the end product will be martensite one. So there is no interaction about this procedure one, this transmission procedure one. So finally we are getting the martensite structure. So it is the lower half of the triple T diagram. So upper half one, the cooling rate is very slow one. After that only we are getting arsenite to pearlitis transformation we can observe. So at slow cooling rate onwards, we can observe the phase transformation austenite to pearlite one. Comes to here, high cooling rate onwards, we can observe the austenite is transformed to martensite. So it is a high cooling rate one. So it is the lower half, upper half of the triple T diagram one. So it is overall concept of the triple T diagram one. So next concept we can see the effect of the alloying elements on the iron carbon alloys one. So the effect of alloying elements on iron carbon alloys one of the effects we can see on alloying elements. By alloying elements we can use it on iron carbon alloys one. So we can see some effects. What are the effects means? See here for analysis, the effect of alloying elements on iron carbon alloys would require analysis of a large number of ternary alloying diagram over a wide range temperature. So it is one of the analysis one. So how can we get how can we know this type of effects means? So how can we know this type of effects means when we analyze, when we can do the analyze on this procedure. So when we do some experiments on this procedure, automatically we can get this type of effects. So at wide range of the temperature, at wide range of temperature onwards, we can see this type of effects. So next one is we ever pointed out the iron iron equilibrium systems fall into the four main stages one. So the binary equilibrium systems fall into the four main categories. So the binary equilibrium systems, it fall into the four main categories. What are the four main categories means? Open, closed, gamma field systems, and expanded and contracted gamma field systems one. First one is open field one, closed system one, gamma field systems one, and expanded contracted gamma field systems one. These four types of categories we can see on the binary equilibrium systems one. So next one is this approach indicates that alloying elements can influence the equilibrium diagrams into two ways. So the in this approach one, so the alloying elements can influence the equilibrium diagrams. So the alloying elements are we can use it for binary phase diagram onwards. Automatically we can see some effects automatically. Why? Because so the alloying elements can influence the binary phase diagrams. Why? Because the phases are based on the alloy elements onwards, the properties, the structure, the composition will be changing onwards. The binary phase diagram you can see clearly the alloying elements. By alloying elements we are using on the binary phase diagrams, automatically we can see some structures changes, so composition changes and properties changes. So next one we can see here that one. So two ways the influence we can see on. So two ways. The first one is the expanding the gamma field and encouraging the formation of the arsenide over wide range composition limits. So these limits are called as the gamma stabilizers. So see here, by expanding when we are expanding the gamma field one and encouraging the formation of arsenide one, so over wider composition limits we are getting one. So this one we can call as the gamma stabilizers. So next one we can see by contracting the gamma field one, so the encouraging the formation of ferrite one over wide range composition limits. So we are getting these limits are called as the alpha stabilizers. So the first one is so gamma field one encouraging the gamma field is encouraging expanding the gamma field one, expanding the gamma field one, encouraging the arsenide one. So over wide range composition limits, so that one we can call as the gamma stabilizer one. So here expanding where gamma field one. So comes to here contracting the gamma field here. In this one expanding, in this one contracting the gamma field one and encouraging the formation of ferrite one. But here encouraging the formation of arsenide one. So after then this one we can call as the gamma stabilizer. So this one we can call as alpha stabilizer. So these are the effects of the alloying elements on iron carbon alloys. So it is our overall topic about the third unit one. So it is the last topic for the third unit one. So comes to the third unit onwards, what we observe third unit means heat treatment procedure. Heat treatment procedure. So any one industry, generally we have the four procedures. The first one is So the first one is the composition and structure one. So next one is properties one. So next one is processing one. So next one is 3-1. First one is structure, composition one. Next one is processing one. So next one is percentage one, carbon percentage. So these three are the very important one. So any industry one you can observe this type of, so this type of variations. When the structure and composition is perfect one, properties is perfect one, so processing is perfect one. So automatically we can see good performance on the one particular material one. So these three are well and good. What is the performance of the material means well and good. The first one is composition and structure. Composition, structure. Second one is, so second one is properties one. So properties are very important one. Structure we are getting, composition we are getting, properties are very important. Next one is processing. In processing onwards we are doing the heat treatment process one. So in processing function onwards we are learning the coordinate one, heat treatment procedure. So heat treatment procedure. So what is the heat treatment procedure means? By using the heat treatment procedure, we want to change the structure and properties. So this is the main one here. Structure, properties, compositions, we are changing one by using the heat treatment procedure one. So in heat treatment procedure, we have this so many methods. The first one is annealing one. Second one is normalizing one. Third one is hardening one. So hardening onwards, we have the classifications. So age hardening. So hardenability also we can observe. So hardenability, age hardening we can see on hardening process onwards. So annealing also we have the few classifications: full annealing, isothermal annealing. So we different types of classifications also we can see on annealing onwards. But normalizing is there is no classifications right topic one. So hardening onwards, so define hardening procedure, hardenability procedures, and age hardening also we can see on hardening one procedures. Next one is tempering one. Tempering also we have the classifications: low tempering, medium tempering, high tempering. So next one is we can see next last topic is surface hardening. So when we are increasing the surface hardness one, so we have the different types of methods. That methods we can discuss about in the previous lecture. So next one is triple T transformation one. Triple T transformation is nothing but time temperature based onwards. The transformation is going on. So that is the one of the topic. So next one is the effect of the alloying elements on iron carbon diagram. So it is the overall coordinate. So overall view of or overall coordinate one, heat treatment procedure. It is one of the last topic. Last topic is effects of alloying elements on iron carbon alloys one. So it is our overall unit one. So tomorrow class onwards we will discuss about fourth unit. So fourth unit is powder metallurgy. So it is the fourth unit one, powder metallurgy. So comes to introduction onwards, powder metallurgy. What is the powder metallurgy? Powder metallurgy may be defined as the art and science of producing metals powders and utilizing them to make a severable object. So metallurgy, single line, we can call as it is one of the art and science, one of the art and science of producing metal powders. So it is one of the art and science of the producing metal powders. So and by using these powders and utilizing these powders, them to make a severable objects. So this one we can call as the powder metallurgy. Powder metallurgy is one of the art and science of the producing metal powders. And by using this metal powders or utilizing these metal powders, so utilize them to make a several object one. So by using this powder and we can utilize this powder to get several objects one. So this one we can call as the powder metallurgy. So see here, or we can call as, it may be also defined as the material processing technique. It is one of the material processing techniques used to consolidated particularly matter, powder both metals or non-metals. Powders are both metals and non-metals. So this one we can call as the powder metallurgy. Powder metallurgy is a simple one we can call as the art and science of producing metal powders. So by using these powders to make several objects is known as the powder metallurgy. Or powder use చేసుకొని we can make so many objects one. So this one we can call as the powder metallurgy. So it is the definition of the powder metallurgy. So next class we will discuss briefly. So the introduction of the powder metallurgy and classifications of the powder metallurgy and methods of powder metallurgy and process of the powder metallurgy we will discuss for next class one. Thank you, Amma. It is our today class one.